so we have our hypotheses set up. Now we want to look at the rest of the metrics that we're going to use in this. So first off, what level of significance should we use? Well, I said usually these are like set by the journal that you're trying to publish in, or industry standards, or some type of governmental regulations, or something like that. Here we're just trying to investigate for the administration itself. We're not trying to publish this necessarily. We're just trying to use this to make an intelligent decision. In that case, and we usually go with the default of 0.05. That's the middle level of significance, right? The common ones were 0.01, 0.05, and 0.10. 0.05 is the one that's in the middle. It's kind of like our balance between how often we're going to make type 1 errors and how often we're going to make type 2 errors. So we'll go with the default 0.05. Now, if you remember, this is kind of equivalent to the confidence levels. Remember I said, well, 95% is the one that's kind of in the middle of 90 and 99%. It gives us a nice balance of having few mistakes and having a reasonably small margin of error. That's the same idea here. So 0.05 is actually a 95% confidence level, right? These are actually equivalent things. So I'm going to use 0.05 here just because I don't really have any reason that I would want a really low one or a high one or anything. This is just kind of a default value when I don't have anything handed to me. So in context, what's the type 1 error here? Well, the type 1 error is, remember, the worst of the two. And when I reject the null hypothesis when it's actually true. Or a different way to think about it, and the way I usually think about it is this way, is that I've supported this claim when this one was the one that's true. So, in context, that means we decide that the mean time taken to graduate is more than 2 years when it actually is 2 years, when this is actually not true. All right, that's all that is. We decide the mean time taken to graduate is more than 2 years when that's not actually true. What about the type 2 error? So this is when the alternative is actually correct, but we weren't able to show it. Well, what does it mean when we weren't able to show it? That means we just didn't have enough evidence. Either our sample mean wasn't high enough above 2, or I just didn't have enough data, right? Because actually, if I've only got like 5 people in my sample, I should expect that to mean I have less evidence than when I have 5,000 people in my sample. So that sample size, as we actually look at conducting these hypothesis tests, will be built into it. So that type 2 error is actually about not having enough evidence. So this would mean, this type 2 error is, the mean is actually more than 2 years, but there's not enough evidence to show it. Right? That's what that is. The mean time taken to graduate is more than 2 years. Like, in reality, it's more than 2 years, but we didn't have enough evidence to support that claim. All right? That's what a type 2 error is. Now, suppose we've got this random sample that had a mean time taken to graduate of 2.2 years. What conclusion can be made? I want to be very, very clear here. There is no point in taking this class. You have learned nothing if you decide that it actually is more than 2 years based purely off of that. Right? Now we're back to just looking at basic sample statistics, just looking at whatever Excel pops out for us, not using any ideas about how samples have natural variability to them, and that from individual to individual things will be different, and I shouldn't expect to get a perfect view of the world from just my sample, right? But when I use this just single point value of 2.2 to make my decision, oh, well, 2.2 is this one. It's more than 2. Well, 2.2 is not the population mean. It's my sample mean. I should make no conclusion at all from that. So the answer to what conclusion can be made from this Nothing. All right? My conclusion is that I haven't wasted my time, at least, with the hypothesis test, because I at least did say, look, I shouldn't even bother with the hypothesis test if there's no evidence in support of this. Well, at least my sample mean does actually seem to suggest that the alternative is true, but now I need to do this hypothesis test to see if that's actually enough evidence. 96 students at 2.2 years for an average, is that enough to say, no, that's not, that 2.2 years isn't just random chance from my sample. I didn't just happen to get people that took longer than 2 years. It's that we've got enough evidence here to actually support that, no, the mean for everybody, the mean for all graduates is actually more than 2 years. All right, that's what we're doing here. And I can't do that with just a single sample mean here by itself. What I need is a p-value and a significance level. That's how I make conclusions. So it says now, okay, well, we arrive at a p-value of 0.09. What decision should I make? Well, I said before we were kind of going to use a default value for my significance level of 0.05. And now I've got a p-value of 0.09. Now, there was something I asked you to highlight, write in bold, cut out, sticks out somewhere, tape it to your desk, like put it on your notebook, whatever it is. And that was, if the p-value is less than your significance level, you're going to reject this and say this is true. Otherwise, don't do that. All right? Well, my p-value is actually not less than my significance level, so I should not be rejecting this. I should not support this conclusion, right? So even though my sample mean made it seem like this might be true, I actually don't have enough evidence to say that couldn't have just happened by just random chance. This really goes back to this kind of, I feel like, intuitive basic idea that if I flip a coin 100 times, I can expect that since there's a 50-50 chance of getting heads, that I'll get around 50. But if I get 51 heads, like, I'm not calling into question that the coin is, like, weighted on one side or the other, right? Or even 52 or 53, those all seem like reasonable numbers. If I start getting 95 heads out of 100, now clearly, like, no, there's something wrong. This coin is, like, illegitimate somehow. That's what we're doing here, is saying, is that mean far enough away from 2 that I can say that really, I guess it's actually more than 2, right? And that it's not just random chance, because by random chance, I'm going to get samples that are above 2 or below 2. I can't just use that sample data by itself. I've got to go through this process of hypothesis testing to evaluate how strong my evidence is. Again, even though I see it all the time by people that honestly just don't have enough training in this, they'll just look at this 2.2 and be like, oh, I guess it's more than 2. That's not how we do things. That's not going to work in general. We'll be making mistakes all the time when we do things like that. That's why we got to use this p-value to measure how much evidence we have. So I'm simply going to not reject the null hypothesis. That should be my decision here, since my p-value is above my significance level. Now, that doesn't mean I've proven this is true. I just said, well, there's not enough evidence to say it's wrong. In other words, I don't have clear and convincing enough evidence to tell me that I should decide the mean's actually more than 2 and take some action about it. So what does that p-value actually mean? All right? So that p-value of 0.09 is the probability that we'd get a sample mean of 2.2 or higher when we assume that the mean is really 2. Okay? Given our sample size, that stuff too. Right? So our p-value here is really just measuring how unusually high a mean of 2.2 would be in our sample when the true mean is actually 2. That's what the p-value does. Measures how unusual our sample is when we assume that the null hypothesis is true. Now, how do we communicate this to lay people? With a sentence like this. And we'll get lots and lots of practice with this. So don't worry about this right now. This is just generally what something like this would look like. So with a p-value of 0.09, there is not enough evidence to support the claim that the mean time taken to graduate at this college, right, it should be referencing our population, is more than 2 years. All right, so what have I done here? I've given the amount of evidence we had, which is a p-value. I've given our actual parameter we investigated, the mean time taken to graduate. I've given the claim we looked at, whether it's more than 2 years, and I gave our actual decision in the test. We didn't have enough evidence to support that, right? That doesn't necessarily mean that this couldn't possibly be true, but that I really should not be supporting this in a statistical sense. So this whole unit is really about establishing a framework, establishing how the steps that we go through make sense, how I proceed from one step to another. It's not about the details of how I knew to write this specific thing out. That will get moving forward. What we want out of this unit is understanding what hypotheses are, what the errors are in a test, why I pick one over the other to be the worst of the two, what a significance level is, and a p-value, like just what these terms mean, not the details of how I write this out. We'll have that in future sections. So I feel like this is a good place to stop. And in the next unit, we'll actually start looking at how to actually do a hypothesis test for a mean, like in this situation.